In the first light of the universe, something red and small is hiding a secret that could rewrite everything we know about black holes. Scientists call them little red dots, and for years, nobody could explain what they were. Some looked like impossible baby galaxies, packed tighter than anything should be able to exist. Others looked like monster black holes, too heavy for their own homes, breaking the rules of growth itself. Today, we chase this mystery from the first dot ever spotted, through a wall of contradictions that stumped the world's best scientists, to a single spiral galaxy that finally cracked the case wide open. We will meet a black hole wrapped in a cocoon of gas thick enough to fool a space telescope, and we will watch scientists drag a galaxy across 10 billion light-years just to prove what it hides. If you like uncovering the universe's deepest secrets, hit subscribe and stay with us. The truth about little red dots is stranger than fiction. Prepare yourselves. We begin. Somewhere in a sea of black, a tiny red speck blinked into a brand new picture of the sky. It was the summer of 2022. The James Webb Space Telescope had just opened its golden eye for the first time, and scientists were scrolling through its first deep pictures like kids opening presents. Most of what they found looked familiar. Spiral galaxies, bright stars, streaks of ancient light. Then someone noticed a strange little smudge, a point of red light sitting where nothing should have been bright enough to see it all. At first, nobody panicked. Space is full of small red dots. Most of the time, that color just means a galaxy is far away, and its light has stretched out on the long trip to Earth, like a siren getting lower pitched as an ambulance drives off. But this dot did not behave like the others. It was too small, too concentrated, too bright for something that old and that far. Astronomers gave it a name, a little red dot. It sounds simple, almost cute. The reality was anything but. Within months, more dots turned up, then dozens, then hundreds, scattered across nearly every deep picture Webb took. Scientists were staring at a population of objects that should barely exist, yet they were everywhere, like a message the universe was trying to send in a language nobody had cracked yet. Here is where the mystery gets strange. Astronomers eventually catalogued 341 of these dots. That is not the discovery of one weird object. That is the discovery of an entire hidden class of things science had never predicted. And the deeper Webb looked, the more of them appeared, packed into pockets of the earliest, darkest chapters of the universe's story. Picture the universe as a 15 billion-mile road trip, with the Big Bang as the starting line. Little red dots showed up almost right at the beginning, when the road trip was less than a tenth of the way done. That is like finding a fully built city on day one of a cross-country drive that is supposed to take months. Something had grown fast, faster than anyone thought was possible. Scientists working on the first dot were not thinking about fame or headlines. They were staring at their screens with a very specific, very human feeling, the feeling of finding something they could not explain. In science, that feeling is not a problem. It is a gift. Confusion is the doorway. Every big discovery in history started with someone staring at data that refused to make sense. So the questions began stacking up immediately. What was this thing made of? Why was it so bright for something so small? Why so early in cosmic history? And most unsettling of all, if this one dot broke the rules, how many more were hiding in plain sight, waiting to be found? Astronomers did not have to wait long for an answer to that last question. The dots kept coming, and each one carried the same eerie signature. Small, red, impossibly dense, and completely unexplained. What started as one strange smudge in a test image was about to become one of the biggest unsolved mysteries in modern astronomy. A puzzle so strange it would eventually make scientists wonder if the universe itself was breaking its own rules. The first little red dot did not answer any questions. It just opened the door, and behind that door was a mystery bigger, stranger, and more dangerous to our understanding of the cosmos than anyone expected. Picture a photograph of the deep sky, filled with thousands of galaxies stretched into ribbons and spirals. Now imagine one point in that picture that refuses to spread out. It stays small, compact. A single glowing speck, no bigger than a pixel or two, even under Webb's most powerful zoom. That is what a little red dot looks like. Not a swirl, not an arm of stars, just a tight, stubborn point of light. Its color is the next clue. In pictures built from Webb's infrared cameras, these objects glow with a deep, blood-red tint. That color is not random. It comes from a very specific pattern in the light, faint in blue and green wavelengths, but suddenly sharply brighter in the red and infrared. Scientists call the shape of that pattern a V, because if you graph the brightness across colors, it dips down, then shoots back up like the letter V drawn in light. Here is a comparison a 15-year-old can picture. Imagine tuning a radio and getting mostly static, except for one narrow band where the signal comes in loud and clear. That is what a little red dot's light looks like to an instrument. Quiet, 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 then a sudden spike. That spike is the fingerprint scientists search for across the entire sky. Size matters here too. Most galaxies you have seen in space photos stretch across huge patches of sky, wide enough to show detail, arms, clusters, glowing centers. A little red dot does none of that. Even at Webb's sharpest resolution, it barely resolves into anything more than a point. Something that small, glowing that brightly, from that far away, is not normal. It is like spotting a single lit window from an airplane at 40,000 feet, and realizing it is somehow as bright as the entire city below it. That contradiction is what makes little red dots so unsettling. Small objects are supposed to be faint. Bright objects are supposed to be big. Little red dots break that rule completely. They are small and blinding at the same time, which immediately tells scientists that whatever is inside them is doing something extreme. There is another detail worth sitting with. Despite the word red in their name, these objects are not simply glowing like a hot coal or a sunset. Real astronomical color is a code, not a paint swatch. When light travels for billions of years across an expanding universe, it stretches. Blue light shifts toward red. So part of what scientists are reading in that red glow is not really about temperature at all. It is about distance and about time. That single fact turns a simple picture into a time machine. The dot is not just showing us light, it is showing us light that started its journey before Earth existed, before our sun existed, when the universe itself was still assembling its first structures. So when scientists look at a little red dot, they are not just seeing a pretty pixel, they are staring at compressed evidence, extreme brightness, extreme compactness, and extreme age, all folded into a single point of red light. And every one of those extremes was about to lead scientists down a very different investigation than they expected. Ask most people why something in space looks red, and they will guess it is hot, or on fire, or glowing like the coils on a stove. In space, that guess is almost always wrong. The redness of a little red dot has almost nothing to do with heat. It has everything to do with motion, distance, and one of the strangest properties of our universe. Everything is moving away from everything else, and that motion changes the color of light itself. Here is the picture. Imagine standing on a sidewalk while an ambulance races past with its siren blaring. As it approaches, the sound waves squeeze together and the pitch sounds higher. As it speeds away, the sound waves stretch out and the pitch drops lower. Light works the same way, except instead of pitch, it is color. As galaxies race away from us, riding the expansion of space itself, their light stretches out, shifting from blue toward red. Astronomers call this redshift. Now stretch that idea across billions of years. The farther away a galaxy is, the longer its light has been stretching, and the redder it appears by the time it reaches Webb's mirrors. So, a red color in a distant image is not a temperature reading. It is a distance reading and a time reading, both at once. This is exactly why little red dots earned their name, and why the name is slightly misleading. Some of that redness really does come from dust, gas, and the physical properties of whatever object is glowing. But a large piece of it comes from an entirely different source: the stretching of light across the vast, expanding gap between that object and Earth. Think of it like listening to a song played backward through a foggy hallway. Some of the muffled sound is because of the fog. Some of it is because the song is being played wrong in the first place. Untangling which part is which, fog or wrong notes, distance or true color, became one of the trickiest parts of solving this mystery. Scientists needed a way to separate these two effects. They needed to know how far away each little red dot actually was, because that number, called redshift, would tell them how far back in time they were looking. The higher the redshift, the earlier the dot existed in the story of the universe. When astronomers ran the numbers, the results were staggering. Many little red dots showed redshifts corresponding to a time when the universe was less than 1 billion years old. Some were even earlier than that. That means the light reaching Webb's cameras in 2022 had been traveling for over 13 billion years, a journey longer than the age of our entire solar system. So every time an astronomer studied one of these dots, they were not just examining a strange object. They were examining a message sent from the deep past, distorted, stretched, and delayed by billions of years of cosmic travel. Understanding that distortion was the first real step toward understanding what these objects actually were. And once scientists nailed down exactly how far back in time they were staring, the mystery only grew stranger. Every telescope is, in a strange way, a time machine. Light does not arrive instantly. It travels at a fixed speed, fast, but not infinite. That means every photograph of space is really a photograph of the past. Look at the sun, and you are seeing it as it looked about 8 minutes ago. Look at a star on the far side of our galaxy, and you might be seeing light that left before humans invented writing. Now, push that idea to its limit. The James Webb Space Telescope was built to catch the faintest, oldest light in existence, light that has been traveling since near the very beginning of time itself. When Webb photographs a little red dot sitting 13 billion light-years away, it is not showing us what that object looks like today. It is showing us what it looked like when the universe itself was practically a newborn. Here is a comparison that makes it click. Imagine mailing a letter to a friend, except the letter takes 13 billion years to arrive. By the time your friend opens it, you have grown up, grown old, and the world has changed completely. But the letter still describes the version of you from the day you wrote it. That is exactly what Webb reads. Ancient letters from ancient galaxies, describing a universe that no longer exists in that form. This is why little red dots caused such an uproar. Scientists were not looking at a strange object nearby. They were looking directly into the universe's childhood at a time period nicknamed Cosmic Dawn, when the first stars and galaxies were only just beginning to light up the darkness. Before Webb, no instrument had ever been powerful enough to see this far back with this much clarity. Earlier telescopes, even the legendary Hubble Space Telescope, could catch glimpses of distant galaxies, but their light was often too faint, too stretched into infrared wavelengths, that Hubble's instruments were not built to capture in detail. Webb was designed specifically to solve that problem, built with a mirror over 6 times the light collecting area of Hubble, tuned to infrared light, the exact wavelengths that ancient, stretched starlight arrives in today. So, when Webb turned its eye toward deep space and immediately started finding hundreds of little red dots, it was not an accident. It was proof the telescope was doing exactly what it was built to do. The problem was not the telescope. The problem was that nobody expected the early universe to look like this. Scientists had models, predictions, educated guesses about how many galaxies should exist that early, how bright they should be, how massive their black holes should be. Little red dots did not fit those predictions. They were too many, too bright, too soon. That mismatch between prediction and reality is exactly the kind of moment that terrifies and thrills scientists in equal measure. It means either the observations are wrong, or the models are wrong, or something deeper is happening that nobody has considered yet. And when a brand new, extremely reliable telescope keeps finding the same strange thing over and over again, the most likely answer is not measurement error. It is a genuine surprise, hiding in the dawn of time, waiting to be understood. If the universe's timeline were stretched into a single calendar year, with the Big Bang happening at the first tick of January 1st, humans would not show up until the last few seconds of December 31st. Galaxies like our Milky Way would not fully form until sometime in the spring, but little red dots start showing up in the first few days of January. That is how early, how shockingly early, these objects appear in cosmic history. In real numbers, most little red dots existed within the universe's first 600 million to 1.6 billion years. Compare that to the universe's current age, about 13.8 billion years, and the picture becomes clear. These objects were some of the very first complex structures to exist. Full stop. Here is a comparison that hits home. Imagine a newborn baby, walking, talking, and holding a full-time job within its first week of life. That is roughly the pace at which little red dots appear to have formed and grown. Structures that should take enormous stretches of time to build, whether packed with stars or anchored by massive black holes, seemed to be fully assembled almost as soon as the universe had cooled down enough to allow anything to form at all. This created what scientists sometimes call a timing problem. Standard models of the universe, built from decades of careful observation and math, predict a certain pace of growth. Small clumps of gas collapse into stars. Stars gather into galaxies. Black holes grow slowly over time by pulling in gas and merging with other black holes. It is supposed to be a marathon, not a sprint. Little red dots looked like they had skipped the marathon entirely and shown up already at the finish line. That single fact, appearing too early, too fully formed, was the first serious crack in the wall of confidence scientists had about how the early universe worked. It gets stranger. Not only did these objects show up early, they showed up in huge numbers almost immediately. It was not one lucky, oddly fast-forming object. It was hundreds of them, scattered across every deep field Webb pointed at, as if speed running the formation of complex structures was somehow common, not rare, in the universe's opening chapter. This is the kind of pattern that makes scientists sit up straight. A single weird exception can often be explained away. A fluke, a mistake, an unusual case. A widespread pattern cannot. If little red dots were common that early, then something about the standard timeline of the universe, the one written into textbooks and computer models, needed a second look. Nobody was ready to throw out decades of well-tested cosmology over one class of strange objects, but nobody could ignore the evidence either. A population of impossibly early, impossibly abundant objects had appeared in the data, and it was not going away. The next step was obvious. Figure out what these things actually were made of. And that investigation would split scientists into two very different camps, arguing over one of the strangest questions in modern astrophysics. Numbers can be dry. Numbers can also be terrifying, depending on what they describe. When astronomers finally tallied up how many little red dots existed in the early universe, the number was not a curiosity. It was an alarm bell. Scientists measure how common something is in space using a number called density, essentially how many of a certain object exist within a given volume of the universe. When researchers calculated the density of little red dots, they found something like 100 times more of them than existing models predicted should exist at quasar-like brightness levels. Not 10% more, not double, roughly 100 times more. Picture ordering a pizza and expecting one slice, only to have the delivery driver hand you an entire stack of 100 pizzas. That is the scale of the mismatch scientists were staring at. Whatever process created little red dots, it was happening far more often and far more efficiently than anyone had modeled. This mattered because scientific models are not guesses pulled out of thin air. They are built on physics that has been tested again and again, on the way gravity pulls matter together, the way gas collapses into stars, the way black holes grow by feeding on the material around them. When observations blow past those models by 2 orders of magnitude, it does not just mean the numbers were slightly off. It suggests a piece of the puzzle is entirely missing. Astronomers began asking a genuinely uncomfortable question. Had the James Webb Space Telescope, this multi-billion-dollar marvel of engineering, actually found a flaw in cosmology itself? Had humanity's best model of how the universe works quietly broken, right at the moment humanity finally built an instrument sharp enough to notice? That question spread quickly through the scientific community and then into public headlines. Cosmology, some said, might be broken. It is a dramatic phrase, and dramatic phrases spread fast. But behind the headlines, most scientists were doing something far less flashy and far more important. They were checking their work again and again, looking for a simpler explanation before assuming the universe itself needed rewriting. That instinct, doubt your own results before doubting the entire foundation of your field, is one of the quiet superpowers of good science. It would take years of careful, patient investigation to figure out whether little red dots were truly breaking the rules of the cosmos, or whether scientists were simply misreading a message sent from 13 billion years in the past. Either way, one thing was clear. An explosion of strange objects spread across the earliest chapter of cosmic history, in numbers nobody predicted, was not something scientists could shrug off. It demanded an explanation, and the first serious attempt at that explanation would take astronomers somewhere both familiar and unsettling. Back to the very basic question of what a galaxy actually is. The simplest explanation is often the first one scientists reach for, and in the case of little red dots, the simplest explanation was stars. Lots and lots of stars, packed into a very small space. Galaxies, at their core, are enormous collections of stars, gas, and dust, all held together by gravity. Our own Milky Way contains somewhere around 100 billion stars, spread across a disk roughly 100,000 light-years wide. If little red dots were simply young, compact galaxies bursting with newborn stars, that would explain the redness. Young star-forming regions often glow through thick clouds of dust, and dust famously scatters blue light away while letting red light pass through, the same reason a sunset on Earth turns fiery orange and red as sunlight filters through more atmosphere. Under this theory, little red dots were essentially cosmic nurseries, dense clusters of baby stars, wrapped in dust, forming at a furious pace in the young universe. It is a tidy explanation, and for a while, it was the leading one. There is something almost comforting about this idea. Stars being born is not exotic. It happens constantly, across the universe, in nebulas and gas clouds everywhere. If little red dots were just extreme, dusty versions of ordinary star formation, then the mystery would not require any new physics. It would just require the early universe to be more efficient at forming stars than anyone expected. But efficient is one thing, impossible is another. And that is exactly where this theory started running into trouble. To match the brightness scientists observed, these star-filled dots would need to pack an almost unbelievable number of stars into an incredibly tiny space, often just a few thousand light-years across, sometimes even less. For comparison, that is a region far smaller than the disk of our own galaxy, yet potentially holding a mass in stars comparable to entire mature galaxies today. Imagine trying to fit the population of an entire country into a single office building. Not impossible to imagine on paper, but physically absurd once you try to picture it happening in real life. That is the kind of density problem the star theory ran into. If little red dots were purely made of stars, they would be some of the densest star systems ever discovered anywhere in the universe, at any point in cosmic history. Some scientists were willing to accept that possibility, arguing that the early universe might have operated under different rules, forming stars faster and more densely than the modern cosmos ever could. Others were far more skeptical. pointing out that no known process could pack that many stars into that little room without the whole structure collapsing or tearing itself apart. The star explanation was not dead, but it was wounded, and that wound was about to open the door to a second, far darker possibility, one involving not stars, but something with far more gravity and far more mystery at the center of every single dot. Numbers rarely feel dangerous, but some numbers, once you understand what they mean, are almost impossible to accept. The density problem at the heart of little red dots is exactly that kind of number. To understand why the star theory struggled, it helps to picture density the way a 15-year-old actually experiences it. Imagine your school gym, and imagine trying to fit every student from every school in your entire state inside it, all standing shoulder to shoulder, no gaps. That packed, uncomfortable, physically extreme scenario is roughly the kind of density scientists were calculating for little red dots. If they were made purely of ordinary stars, real galaxies are not built like that. Even the busiest, most active star-forming galaxies in the modern universe spread their stars across enormous distances, with huge gaps of empty space between star systems. Our own Sun sits roughly 4 light-years from its nearest neighboring star, an almost unimaginable amount of empty space by human standards. Little red dots did not behave like that. Whatever occupied that small, glowing point of light appeared to be crammed into an area far too small for the amount of light and mass scientists were detecting. If it really was stars, entire galaxies worth of stars needed to be squeezed into a region a tiny fraction of the size of a normal galaxy. Gravity has opinions about situations like that. Pack matter too densely, and gravity does not just hold things together gently. It starts crushing things, triggering collapses, mergers, and instabilities that would tear a young star cluster apart before it ever had the chance to look like a calm, glowing dot. This is where astrophysicists started reaching for a different kind of object entirely, something the universe already knows how to compress into incredibly small spaces without falling apart: a black hole. Black holes are, by definition, extreme concentrations of mass in extremely small volume. Unlike a crowd of stars, which needs room to avoid collapsing under its own gravity, a black hole thrives on exactly that kind of collapse. It does not just tolerate extreme density, it is built entirely out of it. If a supermassive black hole sat at the heart of each little red dot, feeding rapidly on surrounding gas and blazing with light in the process, the density problem would practically solve itself. A tiny, unbelievably bright point of light, born from an object that is, by nature, tiny and unbelievably dense. This theory came with its own excitement and its own baggage. Supermassive black holes are supposed to take a long time to grow that large, and little red dots, remember, showed up shockingly early in cosmic history. If black holes really were behind these strange objects, scientists were about to face an entirely new problem, one just as unsettling as the density puzzle they were trying to solve. Every galaxy we know well, including our own Milky Way, appears to hide a supermassive black hole at its very center. Ours, named Sagittarius A star, sits quietly in the middle of the galaxy, roughly 4 million times heavier than our Sun, calmly anchoring the swirl of stars around it. For decades, scientists assumed black holes like this grew slowly, patiently, over billions of years. Little red dots suggested something very different might be happening in the early universe. Instead of a calm, settled black hole quietly anchoring a mature galaxy, these objects look like black holes caught in the middle of a feeding frenzy, still young, still growing, and blazing with light in the process. Here is the picture worth holding on to. A black hole itself gives off no light. It is called black for a reason. But the material spiraling into a black hole, gas, dust, shredded remains of anything nearby, heats up violently as it falls, forming a swirling disk called an accretion disk. That disk can glow brighter than every star in an entire galaxy combined. It is not the black hole shining, it is the meal on its way in. This is the model scientists started favoring for little red dots. Not a galaxy overflowing with stars, but a single supermassive black hole, actively devouring surrounding gas at an extreme rate, wrapped in so much material that the light escaping outward gets filtered, reddened, and concentrated into a single glowing point. Evidence started stacking up in favor of this idea when researchers examined the light coming from little red dots closely, spreading it out into a spectrum the way a prism spreads sunlight into a rainbow. They found something telling. Certain emission lines, specific colors tied to specific chemical elements, appeared unusually wide or broadened. In the vast majority of studied little red dots, somewhere around 70 to 80%, this broadening pattern showed up clearly. That broadening is not decoration, it is a speedometer. Widened emission lines typically mean gas is moving extremely fast, whipping around a source of enormous gravity. Scientists calculated speeds around 2 million miles per hour in that swirling gas, speeds that make sense only near an object with tremendous, concentrated mass. A black hole fits that description, a loose cluster of stars does not. Suddenly, the tiny size, the extreme brightness, and the strange reddened color of little red dots all made sense together. A compact, violently active black hole, feeding fast, glowing bright, wrapped in gas and dust that reddens its light on the way out, exactly like a sunset filtering through smoke. It was an elegant explanation. It solved the density problem. It explained the brightness. It even explained the color. But elegant explanations in science are not the same as proven ones. And this particular black hole theory was about to run headfirst into a contradiction so strange that some scientists worried it might unravel the entire idea. Before going further into the mystery, it helps to understand exactly what scientists mean when they say supermassive black hole, because the term gets thrown around a lot without much explanation. A black hole is a region of space where gravity has become so strong that nothing, not light, not matter, not even information, can escape once it crosses a certain boundary called the event horizon. Ordinary black holes form when massive stars collapse at the end of their lives, and they typically weigh somewhere between a few times and a few dozen times the mass of our sun. Supermassive black holes are an entirely different beast. These monsters can weigh millions, or even billions, of times the mass of our sun, and they sit at the centers of nearly every large galaxy in the universe, including our own. Despite their name, they are not necessarily larger in physical size than expected for their mass. They are simply almost unimaginably heavy. Here is a comparison to make that weight click. If our sun were a single grain of sand, a supermassive black hole with a mass of a few million suns would be like an entire beach compressed down into a space smaller than a marble. That is the kind of concentration we are talking about. Mass so extreme it warps the fabric of space and time around it. Supermassive black holes do not create light on their own. What makes them visible, and sometimes among the brightest objects in the universe, is what happens just outside their event horizon. Gas and dust falling toward a black hole do not fall in a straight line. They spiral, forming a flattened, spinning disk called an accretion disk. Friction and gravitational stress inside that disk heat the material to millions of degrees, and it radiates enormous amounts of energy, sometimes outshining the combined light of every star in the surrounding galaxy. When a supermassive black hole is actively feeding like this, astronomers call the entire glowing system an active galactic nucleus. It is essentially a black hole with the lights on, blazing because of what it is currently consuming, not because of anything intrinsic to the black hole itself. This is the model scientists suspected was hiding inside little red dots, not a passive, sleeping black hole like the one at the center of our own galaxy today, but an active, hungry one, caught in the act of rapid, early growth. Wrapped in the dust and gas it was actively pulling inward. Understanding this distinction matters because it reframes the entire mystery. Little red dots were not just strange objects floating in deep space. If the black hole theory was correct, they were snapshots of supermassive black holes caught during their most violent, most active phase of growth, happening earlier in cosmic history than anyone thought such growth was possible. That single idea, black holes growing to enormous size shockingly fast, was about to collide with one of the most stubborn problems in modern astrophysics, and it would push the mystery of little red dots from strange into something that looked, for a while, genuinely impossible. Here is a rule that has held up across decades of galaxy observations. The mass of a galaxy's central black hole and the mass of the galaxy itself tend to grow together, locked in a kind of cosmic partnership. Bigger galaxies tend to have bigger central black holes. Smaller galaxies tend to have smaller ones. It is not an exact formula, but it is a consistent, well-tested pattern observed again and again in the nearby universe. Little red dots broke that pattern almost immediately. When scientists calculated the mass of the black holes hiding inside these objects and compared it to the mass of the surrounding galaxy, the numbers did not just look unusual, they looked absurd. Some little red dots appeared to host black holes nearly as massive as their entire host galaxy, sometimes representing several percent of the total galactic mass, when the normal expectation from nearby galaxies is closer to a tiny fraction of 1%. Picture a toddler somehow weighing as much as the family truck parked in the driveway. That is roughly the scale of imbalance scientists were staring at. A black hole that should be a small, well-behaved passenger inside its galaxy instead looked like it was making up a shockingly large share of the entire structure's total weight. Scientists gave these objects an appropriately blunt label: overmassive black holes. Not just massive, overmassive, meaning too heavy for the home they were supposedly living in. This mattered because black holes are thought to grow at a maximum natural pace, limited by how fast they can physically pull in and swallow surrounding material without blowing that material away with their own radiation first. There is even a specific speed limit scientists use, called the Eddington limit, essentially the fastest rate a black hole can feed without its own light, pushing incoming gas away like a leaf blower aimed at a pile of leaves. If little red dots really contained black holes this heavy, this early in cosmic history, many of them appeared to require growth rates that pushed right up against, or even exceeded, that theoretical speed limit. It was as if these objects had found some cosmic loophole, growing far faster and far heavier than the physics of accretion was supposed to allow. This is the moment some astronomers started using the phrase broken cosmology, only half joking. Overmassive black holes appearing in huge numbers, shockingly early, growing faster than the rules allowed, was not a minor inconsistency. It looked like a direct challenge to models that had been trusted for decades. Naturally, scientists began hunting for other explanations before assuming physics itself was wrong. Maybe the mass estimates were flawed. Maybe something about these objects was distorting the measurements, making black holes look heavier than they really were. That possibility, that the numbers themselves might be lying, was about to become the center of the entire investigation. But before that idea could take hold, one more piece of evidence arrived, and it made the mystery even harder to explain. If a supermassive black hole is truly feeding at an extreme rate, physics predicts it should be shouting its presence across the universe in a very specific way: X-rays. Gas spiraling into a black hole gets heated to millions of degrees, hot enough to produce not just visible and infrared light, but powerful X-ray radiation as well. In the nearby universe, actively feeding black holes are reliably bright in X-rays. It is one of the most trusted fingerprints astronomers use to confirm a black hole is truly there. So scientists pointed X-ray telescopes at little red dots, fully expecting to catch that fingerprint. What they found instead was almost nothing. Most little red dots showed no significant X-ray emission at all, a silence so total it directly contradicted what the black hole theory predicted. This was a serious problem. Imagine a friend swearing they were at a birthday party, insisting they have photos, receipts, and eyewitnesses. But when you check the surveillance footage, There is no sign of them anywhere in the building. That is roughly the kind of contradiction scientists faced. Every other clue pointed toward an actively feeding black hole. The X-rays, the single most reliable piece of confirming evidence, simply were not there. Some researchers wondered if this missing evidence meant the black hole theory was wrong entirely, pushing some scientists back toward the star-heavy explanation, despite its own density problems. If little red dots were not black holes after all, maybe they really were unusually dense, unusually dusty pockets of extreme star formation, somehow avoiding the physical collapse that seemed to make that idea so difficult to accept. Other scientists suspected something different. Perhaps the black holes were real, feeding exactly as predicted, but something was blocking their X-rays from ever reaching Webb's instruments in the first place. Not an absence of evidence, but evidence being actively hidden. This idea led scientists toward the concept of obscuration, the possibility that little red dots were wrapped in such thick layers of gas and dust that even powerful X-rays, normally capable of punching through enormous amounts of material, were being absorbed before they could escape. It is a bit like a car alarm going off inside a bank vault. The alarm is still blaring. It is simply too muffled by the walls around it to be heard outside. If little red dots were essentially black holes hidden inside cosmic vaults of gas, their missing X-rays would not disprove their existence. It would just mean scientists needed better tools and cleverer methods to detect the muffled signal hiding behind the silence. This missing X-ray puzzle became one of the defining contradictions of the entire little red dot mystery. It did not just add confusion, it forced scientists to reconsider what these objects actually looked like from the inside, wrapped in mystery layers nobody could yet see through. By this point in the investigation, little red dots had earned a strange reputation. They looked like one thing under one kind of observation, and something completely different under another. Scientists started describing them almost like a classic literary character, living a double life, calm and ordinary on the surface, but hiding something far more volatile underneath. Look at their spectra. The rainbow of light spread out to reveal chemical fingerprints, and little red dots practically screamed active black hole. Broad, fast-moving gas. Telltale emission lines. All the classic signatures astronomers use to identify feeding supermassive black holes elsewhere in the universe. But look at their X-ray signal, normally one of the most dependable black hole indicators available, and little red dots went almost completely silent, behaving instead like the calm, exotic star clusters some scientists still argued for. This contradiction was not a minor inconvenience. It struck at the heart of how astronomers identify objects in deep space in the first place. Normally, when multiple types of evidence point toward the same conclusion, confidence builds quickly. With little red dots, different types of evidence pointed in opposite directions entirely, as if the universe were deliberately handing scientists a puzzle with mismatched pieces. Picture meeting someone who, in every conversation, sounds calm, friendly, and completely unremarkable, yet every camera that tries to photograph them comes back blurry, distorted, or strangely dark. You would not necessarily assume something supernatural is happening. You would start suspecting there is something about the environment, the lighting, the distance, or the equipment itself, actively distorting what you are able to observe. That is exactly the mindset astronomers adopted. Rather than assuming little red dots were some entirely new category of object defying known physics, many researchers began focusing on a more grounded question. What if the object itself was fairly ordinary, but something surrounding it, some environmental factor, was warping the signals scientists were trying to read? This shift in thinking mattered enormously. It moved the investigation away from asking simply, "What are little red dots?" and toward a more specific, more solvable question. What is happening around little red dots that could explain why they look so wildly different depending on how you study them? That question pointed directly at the thick, mysterious material many scientists suspected was wrapped around these objects, potentially reddening their light, muffling their X-rays, and distorting the very measurements meant to reveal their true nature. It was time to take that gas cocoon idea seriously and follow it as far as the evidence would allow. If little red dots really were behaving like a cosmic Jekyll and Hyde, one obvious suspect was standing in plain sight: the material surrounding them. Scientists began seriously exploring the idea that each little red dot might contain an actively feeding black hole, wrapped inside an extraordinarily dense, extraordinarily thick cocoon of ionized gas. Ionized gas simply means gas that has had electrons stripped away from its atoms, leaving behind a charged, energetic soup of particles. In small amounts, ionized gas is common throughout the universe, but the amount scientists were now proposing around little red dots was anything but small. Some models required electron densities so extreme and cocoon sizes so compact that the only way to explain the observed brightness and behavior was a black hole practically drowning in its own surrounding material. Picture a light bulb wrapped not in a thin lampshade, but in dozens of layers of thick, foggy glass. Some light still gets through, but it comes out dimmer, redder, and completely unable to show you clearly what the bulb underneath actually looks like. That is roughly the role scientists proposed for this gas cocoon, filtering and distorting the black hole's true signal before it ever reached Webb's instruments. This cocoon idea elegantly solved several problems at once. It explained the reddened color, since thick gas naturally scatters and absorbs blue light more effectively than red light. It explained the missing X-rays, since sufficiently dense material could absorb X-ray photons before they ever escaped. And it explained the confusing, contradictory signals scientists kept finding, since different types of light were being filtered differently on their way out through the cocoon. There was still a problem though, and it was a big one. To explain everything scientists were observing, these gas cocoons needed to be almost impossibly dense, compressed into regions, sometimes measured not in light years, but in light days, a scale of distance roughly comparable to the size of our own solar system. That kind of density is difficult to picture, so try this. Imagine compressing the entire population of Earth, all 8 billion people, down into a single football stadium, then imagining that stadium is somehow still standing under that crushing weight. Extreme density like that does not usually stay stable. It tends to either collapse further or blow apart entirely. Scientists needed a way to actually test whether gas this dense could exist around little red dots, rather than just theorizing about it. That test would come from an unexpected place, not from photographing the dots more clearly, but from looking incredibly closely at the subtle shape of the light itself, down to the width of individual spectral lines. And that closer look was about to change everything scientists thought they knew about how heavy these black holes actually were. To understand the next major breakthrough, it helps to understand a strange but simple idea. Light can get shoved around by crowds of electrons, the same way a person walking through a packed concert crowd gets bumped, jostled, and slowed down before finally reaching the exit. This phenomenon is called electron scattering, when light particles, called photons, travel through an extremely dense cloud of free-floating electrons. They do not always travel in a straight line. They bounce, collide, and scatter off those electrons before continuing on their journey. Each tiny collision nudges the photon's direction and energy slightly, and across an enormous crowd of electrons, those tiny nudges add up into something scientists can actually measure. Here is why this mattered enormously for little red dots. For years, scientists estimated the mass of the black holes inside these objects, using a method built on a different phenomenon entirely: the width of certain spectral lines, interpreted as a measurement of how fast gas was orbiting the black hole. Wider lines were assumed to mean faster orbiting gas, and faster orbiting gas was assumed to mean a heavier black hole, since it takes more gravity to whip material around at higher speeds. But electron scattering can widen spectral lines too, without any of that gas actually needing to move faster at all. Picture two different ways to blur a photograph. One way is genuine motion, someone running quickly across the frame while the shutter is open. The other way is simply smudging the lens itself, blurring the picture even if nothing in the scene ever moved. Both produce a blurry photo. Only one of them actually involved speed. For years, scientists had been reading blurred, broadened light from little red dots and assuming it meant extremely fast-moving gas, which meant extremely heavy black holes. Electron scattering raised an uncomfortable possibility. What if some, or even most, of that blurring was really just smudging, caused by a thick cocoon of electrons scattering the light on its way out, with no need for such extreme black hole masses at all? If true, this would not just tweak the numbers slightly. It would mean scientists had been systematically overestimating the mass of black holes inside little red dots, possibly by a significant amount, simply because they had been misreading the cause of the blur. This was not just a theoretical possibility anymore. Researchers began digging through Webb's highest quality spectra, searching for the subtle signature that would prove electron scattering, rather than pure orbital speed, was responsible for the strange broadened lines seen across the little red dot population. What they found would become one of the single biggest turning points in the entire investigation, forcing astronomers to rewrite the numbers behind one of the strangest mysteries Webb had ever uncovered. In January of 2026, a team of researchers led by scientist Vadim Rusakov published a study that changed the entire conversation around little red dots. Using some of the sharpest spectra Webb had ever captured, the team carefully examined the shape of the broadened lines coming from these mysterious objects, hunting specifically for the fingerprint of electron scattering. They found exactly what the theory predicted. In most of the little red dots studied with the highest quality data, the broadened lines showed a distinctive shape, a narrow, sharp core of light, surrounded by wider wings stretching outward. That specific shape is the signature of electron scattering, not pure high-speed orbital motion. It meant photons really were bouncing through a dense, compact cocoon of electrons on their way out, exactly like light scattering through thick fog. The implications were enormous. Once the team accounted for scattering instead of assuming pure motion, the true orbital speeds implied by the narrow line cores were dramatically lower than previous estimates. And lower orbital speeds mean lower black hole mass, since it takes far less gravity to explain gently orbiting gas than wildly fast orbiting gas. The new estimates were staggering in the opposite direction from where the mystery began. Instead of overmassive monsters, weighing close to a significant fraction of their entire host galaxy, the true black hole masses came out roughly 100 times lower than earlier calculations had suggested, landing somewhere in the range of 100,000 to 10 million times the mass of our Sun. Picture believing you were staring at a beach ball, only to discover, once the fog cleared, that you were actually looking at a marble the whole time, magnified and blurred by everything standing between you and it. That is essentially what happened to the black hole mass problem. The objects were still real, still fascinating, still active and feeding. They were simply never as impossibly, physics-breaking heavy as the earliest calculations suggested. This discovery did something remarkable to the overmassive black hole crisis. It did not eliminate it completely, but it dramatically eased the tension. Black holes in the range of 100,000 to a few million solar masses fit far more comfortably within existing models of early black hole growth than black holes weighing a meaningful fraction of their entire galaxy. For the scientists who had spent years worrying that cosmology itself might be broken, this was a genuine sigh of relief. The universe had not necessarily rewritten its own rulebook. Scientists had simply been misreading a blurred signal, mistaking fog for speed and speed for mass. But easing the crisis is not the same as solving the mystery completely. Even with corrected, lower masses, little red dots were still strange, still compact, still wrapped in dense gas cocoons nobody fully understood. The investigation was not over. If anything, it had just entered its most important chapter yet, because now scientists needed to explain not just what these objects weighed, but why they seem to vanish so completely from the more recent universe. 100 times lighter sounds like it should have solved everything. In some ways, it did. But recalculating the mass of these black holes did not answer every question sitting on the table. It simply removed one very specific, very dramatic contradiction, while leaving several other mysteries fully intact. Consider the missing X-rays. A lighter black hole does not automatically explain why so many little red dots remained almost completely dark in X-ray observations. The dense electron cocoon responsible for scattering their light could plausibly explain that silence too, but that still meant scientists needed to prove, in detail, that gas this thick and this compact could genuinely exist, form, and survive around a feeding black hole without collapsing or dispersing. Consider the timing problem as well. Even smaller, less extreme black holes still needed to form and grow shockingly fast within the universe's first several 100 million years, faster than many standard models of black hole seed growth comfortably allowed. Solving the mass problem eased the crisis. It did not erase the underlying pressure of building something this complex this early in cosmic history. Here is a comparison that captures the moment. Imagine a police investigation where new evidence proves the suspect is not, in fact, 7 feet tall and superhumanly strong, as first reported. That is real progress. It rules out an impossible scenario, but it does not automatically explain how the suspect vanished from every security camera in the building, or how they moved through a locked door. Some mysteries remain even after the most dramatic claim gets corrected. For little red dots, the biggest remaining mystery was about to become the strangest one yet. These objects appeared in massive numbers early in cosmic history, and then, as the universe continued aging, they seemed to disappear almost entirely, not gradually fading into a different category of object, but essentially vanishing from view within a relatively narrow window of cosmic time. That disappearance troubled scientists just as deeply as the overmassive black hole problem ever did. If little red dots represented a genuine, common phase of black hole growth in the early universe, where did they go afterward? Black holes do not simply blink out of existence. Whatever these objects evolved into, or transformed from, needed an explanation grounded in real physics, not convenient guesswork. The corrected black hole masses had cleared away one obstacle blocking that search. Now, scientists could focus more clearly on the next, and arguably more fascinating, question. Not just what are little red dots, but where does an entire population of ancient, actively feeding black holes go once the early universe's chaotic, gas-rich chapter finally starts to calm down? Every good mystery needs a disappearance, and little red dots delivered one of the strangest disappearances in modern astronomy. These objects showed up in massive numbers during the universe's first 2 billion years. Then, as the cosmic clock kept ticking forward, they seemed to fade out almost entirely, dropping in number by roughly 2 orders of magnitude between an earlier era and a later one. 2 orders of magnitude is not a small drop. It means roughly 100 times fewer little red dots showed up in later cosmic history compared to their peak. Picture a species of animal that fills an entire forest with thousands of sightings every year, then suddenly, within a few generations, drops down to just a handful of confirmed sightings across the entire region. Something had clearly changed, and scientists needed to know whether that change was real or an illusion created by the limits of observation itself. This is where the investigation split into 2 very different possibilities, each with major consequences. The first possibility, little red dots were a genuine, short-lived phase in cosmic history. Under this idea, black holes really did go through an early, active, little red dot stage, then transformed into something else as the universe aged, meaning the disappearance reflected real physical evolution, not a trick of the telescope. The second possibility was far more unsettling for scientists who study distant objects for a living. What if little red dots never actually disappeared at all? What if they simply became too faint, too distant, or too disguised for even Webb to detect once the universe reached certain later stages? Under this scenario, the vanishing act would not be evidence of evolution. It would be evidence of a blind spot, a gap in what any telescope, no matter how powerful, can actually observe across the staggering distances involved. This distinction mattered enormously. If little red dots were a genuine short-lived phase, then understanding why they appear and disappear would teach scientists something entirely new about how supermassive black holes are born and grow. If instead they were an observational illusion, then the entire population might still be out there, hiding in plain sight, simply too far away or too disguised for existing tools to catch. Complicating things further, some newer surveys found the drop was not quite as steep as first believed. Certain studies, using different detection methods, found little red dots persisting later into cosmic history than initial estimates suggested, at what astronomers call cosmic noon, roughly 10 to 11 billion years ago, a time when galaxy formation across the universe was at its most furious and active. That inconsistency between different studies was itself a clue. It suggested the disappearance might depend heavily on exactly how astronomers were searching and exactly what kind of light they were looking for. Some little red dots might genuinely be rarer at later times. Others might simply be slipping through the cracks of detection methods not built to catch them. Solving this puzzle would require more than better math. It would require finding a little red dot close enough and clear enough for scientists to study in full detail, without the extreme distances of the early universe distorting every measurement along the way. That search was about to become the most important hunt in the entire little red dot story. By early 2026, the phrase broken cosmology had leaked out of research papers and into public conversation. Headlines picked it up. Online debates multiplied. For a field built on careful, patient measurement, this kind of viral attention created real pressure, both exciting and uncomfortable at the same time. It is worth understanding why this phrase spread so fast. Cosmology is not just an abstract academic subject. It is the framework underneath essentially every claim scientists make about the origin, age, and future of the universe. If little red dots truly proved that framework wrong in ways nobody had predicted, the implications would ripple outward into nearly every corner of astrophysics. Imagine discovering a single, small crack in the foundation of a skyscraper. Even a small crack raises an unavoidable question: how much of the building above it can still be trusted? That is roughly the anxiety little red dots created among cosmologists. If the standard model failed to predict such a large, abundant population of overmassive black holes this early in cosmic history, what other predictions might be wrong too? At the same time, most working scientists understood something the public conversation often missed. Extraordinary claims require extraordinary evidence, and a handful of confusing new objects, however strange, were not automatically proof that decades of carefully tested cosmology needed to be thrown out. Science has a long history of objects that looked impossible at first, only to be explained later through better data, better instruments, or corrected assumptions without requiring new physics at all. This is precisely why the scientific process moves the way it does. Instead of rushing to declare cosmology broken, researchers kept gathering more data, testing competing explanations, and stress testing their own assumptions. The electron scattering discovery, lowering black hole mass estimates by roughly 100 times, was a perfect example of this process working exactly as intended. A crisis that looked catastrophic on the surface eased significantly once scientists found and corrected a flawed assumption hiding underneath the data. Still, easing a crisis is different from closing a case file. Even with corrected masses, little red dots remained a genuinely new, genuinely surprising population of objects. Unlike anything catalogued before Webb existed, their abundance was still higher than predicted. Their formation timeline was still uncomfortably fast, and their eventual disappearance from the more recent universe remained completely unexplained. Scientists needed something more powerful than another spectrum, another mass calculation, or another theoretical model. They needed a real-world example, an actual little red dot sitting close enough to Earth that its surrounding environment could finally be seen clearly, rather than inferred through indirect, distance-blurred clues. Finding an object like that would not just add one more data point to a growing catalogue. It had the potential to answer nearly every open question at once. What these objects really are, why they look so contradictory, and what happens to them as the universe grows older. The hunt for exactly that kind of object was already quietly underway. Searching for a nearby little red dot sounds simple in theory. In practice, it is closer to searching for a single specific grain of sand, scattered somewhere among an entire beach of ordinary-looking pixels, buried inside years of archived telescope data. Here is the core challenge. Nearly every confirmed little red dot sat at extreme distances, corresponding to a time when the universe was less than 2 billion years old. Objects that far away are, almost by definition, difficult to study in detail. Their surrounding structure gets washed out by distance, their light gets stretched and dimmed, and separating the object itself from its environment becomes nearly impossible. What scientists needed was something rarer, a little red dot, or an object closely resembling one, sitting at a much smaller cosmic distance, ideally somewhere in the range of a few billion light-years, rather than 10 or more. An object like that would still be far enough away to have formed early enough to matter, but close enough that Webb's cameras could resolve real detail around it, rather than just a single blurred point of light. Think of it like trying to understand what a specific breed of bird looks like using only distant, blurry photographs taken from miles away, versus finally spotting one perched on a branch just outside your window. The distant photos might hint at shape and color. Only the close-up view reveals the details that actually explain how the bird lives, hunts, and behaves. Researchers began combing through years of archived Webb observations, searching not just newly targeted images, but old survey data originally collected for entirely different purposes. Space telescopes generate enormous amounts of data, often observing far more of the sky than any single research team can fully analyze in real time. Buried inside those archives, unexplored details sometimes wait years before anyone notices their significance. This kind of archival digging is unglamorous work. It does not involve dramatic new observations or headline-grabbing announcements. It involves patiently sorting through catalogs, cross-referencing coordinates, and checking whether any previously known objects might secretly match the telltale signature of a little red dot hiding in plain sight simply because nobody had looked closely enough before. Eventually, that patient searching paid off. Buried inside archival data from one of Webb's major deep field surveys, researchers found something extraordinary: a spiral galaxy sitting at a much closer distance than any confirmed little red dot before it, with a small, intensely bright, suspiciously red nucleus glowing at its very center. It was not a coincidence that instruments happened to capture this galaxy in exactly the right way, but it was, in many ways, a stroke of luck that this particular galaxy existed at all, sitting at exactly the right distance to test everything scientists suspected about little red dots. Researchers gave this galaxy a nickname that would soon become central to solving one of astronomy's biggest recent mysteries, the saguaro. The saguaro did not look like a mystery at first glance. It looked like an ordinary spiral galaxy, complete with sweeping arms of stars, active regions of star formation, and a broad, extended disk, the kind of galaxy astronomers have studied thousands of times before. Its official catalogue name, a long string of letters and numbers, gave no hint of anything unusual. Its nickname came from something far simpler. Its prominent, sweeping arms reminded researchers of a towering desert cactus. What made the saguaro remarkable was not its outer appearance. It was what sat glowing at its very center. Nestled deep inside this ordinary-looking spiral galaxy was a compact, intensely bright, distinctly red nucleus, matching the exact signature scientists had spent years chasing across the early universe. Here is why that mattered so much. The saguaro sat at a redshift corresponding to roughly 10.4 billion years ago, about 3.3 billion years after the Big Bang. That is still ancient by human standards, older than our entire solar system, but compared to the extreme distances of most confirmed little red dots, sitting closer to 13 billion years back, the saguaro was practically next door. Picture the difference between studying a crime scene from grainy security footage recorded miles away versus finally getting a clear, close-up photograph of the exact same event. The saguaro offered exactly that upgrade, close enough to reveal detail, old enough to still carry the same essential fingerprint scientists had been chasing. There was a lucky twist buried in how this discovery even happened. One of Webb's precise spectroscopic instruments, called a microshutter array, happened to be aligned directly over the saguaro's core during an entirely different observing program, part of a major survey scanning a specific patch of deep sky. Nobody was specifically hunting for this galaxy when the data was collected. It was simply sitting there, already captured, waiting inside the archive for someone to notice its significance. This is one of the quieter truths about modern astronomy. Major discoveries do not always come from brand new observations built specifically to test a single hypothesis. Sometimes they come from returning to existing data with a fresh question in mind, finding meaning in information that had been sitting untouched for months or even years. Once researchers realized what they were looking at, the excitement was immediate. If the saguaro's glowing nucleus truly matched the defining characteristics of a little red dot, and if its surrounding spiral structure could be studied in full detail, scientists finally had a real, physical example to test every theory built up over the previous several years. It was time to look closely, separate the galaxy's outer structure from its glowing heart, and find out once and for all whether this ordinary-looking spiral galaxy was hiding one of the universe's strangest secrets in plain sight. Finding one galaxy in the right place, at the right distance, with the right kind of glowing center, might sound like simple good fortune. In some ways, it was. But the saguaro's usefulness went far beyond just being conveniently located. Its specific position in cosmic history made it almost perfectly suited to answer the exact questions scientists had been struggling with for years. Consider the timing. The saguaro existed roughly 3.3 billion years after the Big Bang, placing it well after the earliest wave of little red dots, but still early enough to plausibly represent a slightly later stage of the same evolutionary story. If little red dots really do transform into something else as the universe ages, an object like the saguaro sat in exactly the right window to potentially catch that transformation caught in progress. Consider the distance next. Far enough away to still carry a meaningfully high redshift, confirming it belonged to a genuinely ancient population of galaxies. Close enough, however, that its light had not stretched and dimmed so severely that its surrounding structure disappeared entirely, the way it does for the earliest, most distant little red dots. Here is a comparison worth holding on to. Imagine trying to understand what a caterpillar becomes by only ever seeing very young caterpillars and very old butterflies, with nothing observable in between. You could guess at the transformation, but you could never actually see it happening. The saguaro offered something closer to catching a chrysalis mid-transformation, a genuine snapshot of a process otherwise hidden between two extremes. There was also a practical advantage baked into the saguaro's discovery. Because Webb's instruments had already captured detailed spectroscopic data across this galaxy's core, almost by accident, researchers did not need to schedule brand new, highly competitive observing time on the telescope, a process that can take months or years to secure. The data already existed, sitting quietly in an archive, ready to be analyzed with fresh eyes. None of this diminished the discovery's importance. If anything, it highlighted something valuable about how science actually progresses. Sometimes breakthroughs depend less on building bigger, more expensive instruments, and more on returning to existing evidence with better questions, sharper theories, and a clearer sense of exactly what to look for. With the saguaro identified and its data ready for deeper analysis, the real work could finally begin. Researchers needed to carefully separate the galaxy's broader structure, its spiral arms, its star-forming regions, its extended disk, from the single, compact, intensely bright nucleus sitting at its center. Only by isolating that nucleus completely could they test whether it truly matched the little red dot signature, or whether the resemblance was simply a coincidence waiting to fall apart under closer inspection. Studying a galaxy's central nucleus is not as simple as pointing a telescope and reading off a single number. Light from the surrounding galaxy, its stars, its gas, its dust, all blends together with light from the nucleus itself, especially from extreme distances where fine detail becomes difficult to resolve. To truly understand what was happening at the saguaro's heart, researchers needed a way to cleanly separate these overlapping sources of light. Here is a comparison that makes the challenge clear. Imagine trying to isolate a single trumpet sound from within a full live orchestra recording, without access to the original separate instrument tracks. You would need extremely careful techniques, precise filtering, and detailed knowledge of exactly what a trumpet sounds like in order to pull that one instrument's contribution out of the combined performance. Astronomers faced a strikingly similar challenge, separating one glowing point of light from the wash of an entire galaxy's worth of stars. Because the saguaro sat at a relatively close, well-resolved distance, Webb's cameras, combined with detailed archival data from the Hubble Space Telescope, could actually distinguish individual components within the galaxy. Researchers could trace the shape and brightness of the spiral arms separately from the compact glow sitting at the very center. Once that separation was complete, the results were unmistakable. The nucleus, alone, isolated from its surrounding galaxy, displayed exactly the defining V-shaped spectral pattern scientists had spent years searching for, dim in blue and green light, then sharply, unmistakably brighter in red and infrared wavelengths. This was not a vague, approximate match. It was a precise, confirmed signature, the same distinctive V-shape scientists had painstakingly identified across hundreds of distant, blurred, difficult-to-study little red dots. Except this time, the signature was coming from a nucleus. Scientists could see clearly, embedded inside a fully visible, fully understood host galaxy. Picture finally matching a blurry, partial fingerprint from an old case file against a clean, complete fingerprint taken directly from a real, identifiable source. That is roughly the level of confirmation this moment represented. The saguaro's nucleus was not just similar to a little red dot. By every measurable signature scientists knew how to test, it was one. This discovery mattered enormously because it proved something researchers had suspected but never directly confirmed. Little red dots are not necessarily strange. Standalone objects existing in isolation, they can exist at the center of completely ordinary-looking spiral galaxies, hidden in plain sight, indistinguishable from their host. Once, distance and surface brightness, dimming strip away everything except their brightest, most compact core. With the nucleus confirmed as a genuine little red dot match, researchers had one more crucial test to run. If this really was an actively feeding black hole, hidden inside thick surrounding material, it should still be hiding a faint signature of X-ray emission, the same missing evidence that had haunted the entire investigation from the very beginning. For years, missing X-rays had been one of the most stubborn contradictions in the entire little red dot mystery. If these objects truly contained actively feeding black holes, physics predicted they should glow in X-rays. Yet observation after observation came back nearly silent. The saguaro offered researchers a chance to finally test this contradiction directly, using an instrument built specifically to catch exactly this kind of high-energy light, NASA's Chandra X-ray Observatory. Chandra pointed its sensitive detectors toward the saguaro's core, searching for any trace of X-ray emission coming from that glowing red nucleus. This time, unlike so many previous attempts across the broader little red dot population, something showed up, faint, weak, easy to miss if you were not looking carefully. but present. This detail mattered enormously. A completely dark, X-ray silent nucleus might have suggested the entire black hole theory was wrong after all. A faint, but genuinely detectable signal told a very different story. Not an absence of X-rays, but a heavily muffled one, exactly what scientists would expect from a black hole buried inside thick layers of obscuring gas and dust. Picture standing outside a concert hall with thick, soundproofed walls. You cannot clearly make out individual instruments or lyrics, but if you listen closely enough, you can still detect a faint, muffled rhythm leaking through the barrier. Unmistakable proof that a loud, active performance is happening just out of clear reach. That faint rhythm is exactly the kind of signal Chandra picked up from the saguaro. Researchers involved in the study were careful in how they described this result, avoiding overblown claims while still recognizing its significance. Caris Gilbert, a researcher involved in the project, explained that this specific combination, meaningful obscuration paired with weak but present X-ray emission, could help explain the puzzling silence seen across nearly the entire broader little red dot population. This finding effectively completed a full circle of evidence. The nucleus matched the defining color signature of a little red dot. Its surrounding environment showed the kind of thick, obscuring material capable of muffling X-rays without eliminating them completely. And the faint, but real, X-ray detection matched almost exactly what an obscured, actively feeding black hole should produce. For years, missing X-rays had felt like a fatal flaw undermining the entire black hole theory. The saguaro suggested something far less dramatic and far more satisfying, scientifically. The X-rays were never truly gone. They were simply hidden, muffled by exactly the kind of dense material scientists had already suspected surrounded these objects all along. With every individual piece of evidence now falling into place, researchers were ready to attempt the most ambitious test of all. Rather than simply studying the saguaro as it currently appeared, they would mathematically drag this entire galaxy across billions of additional light years, simulating exactly what Webb would see if this same object sat at the extreme distances where most little red dots are actually found. Every previous piece of evidence pointed toward the same conclusion, but researchers wanted something more than a strong hint. They wanted direct, undeniable proof. So they designed an experiment that sounds almost like science fiction. Take the fully resolved, fully understood saguaro galaxy and mathematically simulate what it would look like if it were moved to the same extreme distance as a typical early universe little red dot. This is not the same as physically moving a galaxy, which is obviously impossible. Instead, researchers use detailed models of how light behaves across an expanding universe, accounting for distance, redshift, and the physics of how brightness fades over cosmic scales to calculate exactly what Webb's instruments would detect if the saguaro sat roughly 13 billion light-years away instead of its actual distance of 10.4 billion light-years. Picture taking a detailed, close-up photograph of a mountain, complete with visible trees, rock formations, and hiking trails. Then, using precise mathematical rules to calculate exactly what that same mountain would look like from an airplane window, far higher up and far farther away. The mountain itself does not change. What changes is how much detail remains visible once distance and altitude are added into the equation. Researchers ran this simulation carefully, applying the same physical principles that govern how real telescopes observe real distant objects. Once complete, they compared their simulated, distant version of the saguaro against real observations of actual, confirmed, little red dots from the early universe. The results were striking. In the simulated, distant version, the galaxy's sweeping spiral arms, its visible star-forming regions, its broad, extended disk, all of it dropped completely below Webb's ability to detect. Only one single feature remained visible: the compact, intensely bright red nucleus at the very center. That remaining point of light was, by every measurable characteristic, indistinguishable from any of the 341 confirmed little red dots already catalogued across Webb's deep field surveys. Same size, same brightness pattern, same telltale red signature. This was not a subtle, ambiguous result requiring careful interpretation. It was about as close to a direct demonstration as astronomy ever gets. A real, fully understood spiral galaxy, when mathematically pushed to extreme cosmic distance, transformed into something that looked exactly like the mysterious objects scientists had been chasing for years. Researchers now had something far more powerful than another theoretical model. They had direct proof of mechanism, a working demonstration of exactly how and exactly why an ordinary spiral galaxy could disguise itself as a strange, isolated point of light simply by sitting far enough away. The simulation results demanded a deeper explanation. Why would an entire galaxy's worth of stars, spiral arms, and star-forming regions simply vanish from view, while a single, compact nucleus remained perfectly visible across the exact same enormous distance? The answer comes down to a basic, often overlooked property of how brightness behaves differently depending on an object's size and shape. Extended objects, things that cover an area, like a galaxy's disk or spiral arms, dim dramatically faster with distance than compact, point-like objects do. Here is a comparison that makes this click immediately. Imagine two light sources, a small, extremely bright flashlight bulb, and a large, softly glowing sheet of light the size of a bedroom wall. Move both light sources progressively farther away, and something interesting happens. The small, concentrated flashlight remains visible from a much greater distance than the large, spread-out glowing sheet, even if both start out equally bright up close. Concentrated light survives distance better than spread-out light. Little red dots surrounding galaxies behave exactly like that glowing sheet. Their light is spread out across a relatively wide area, faint to begin with, and it dims extremely quickly as distance increases. Their central compact nucleus, by contrast, behaves more like that small, bright flashlight, concentrated enough to remain detectable across staggering cosmic distances that completely erase everything spread out around it. This effect follows a specific mathematical rule scientists call cosmological surface brightness dimming, tied closely to redshift. Without diving into complicated math, the practical result is straightforward. As redshift increases, an extended object's visible brightness drops off far more steeply than a compact object's does. At sufficiently high redshift, this difference becomes so extreme that entire galaxies effectively disappear from a telescope's view, while their compact, glowing centers remain fully detectable. This single physical principle solved an enormous piece of the little red dot mystery. Little red dots were never necessarily standalone, isolated objects, floating in empty space with no surrounding galaxy at all. Many of them likely sit at the center of fully formed, ordinary-looking host galaxies, identical in spirit to the Saguaro, simply too far away for Webb or any current telescope to detect anything beyond their brightest, most concentrated core. Picture receiving a photograph so distant and so degraded that only a single glowing pixel remains visible, with everything else fading into pure black background noise. You are not looking at evidence that nothing else exists in that picture. You are looking at the practical limit of what your camera, however powerful, can actually capture across that specific distance. This reframing changed everything about how scientists needed to think about the entire little red dot population. The mystery was never really about what these objects are missing. It was about what distance itself was hiding from view all along. It helps to sit for a moment with exactly how extreme this dimming effect really is, because the numbers involved are almost hard to believe. For an extended object like a galaxy's disk, surface brightness dims according to a factor tied to redshift raised to the fourth power. At a redshift of 7, corresponding to roughly 700 million years after the Big Bang, that dimming factor works out to be over 4,000 times fainter than the same galaxy would appear if it were sitting at essentially zero distance. 4,000 times fainter is not a subtle effect. Picture a lamp bright enough to comfortably light an entire room. Then imagine that same lamp dimmed down to a level so faint you would need to sit in complete darkness, eyes fully adjusted, just to detect the faintest hint of its glow. That is the scale of dimming affecting an extended galaxy's disk at these extreme cosmic distances. Compact, point-like sources behave completely differently. Instead of dimming with that harsh fourth-power relationship, their brightness fades following a gentler rule, tied closer to redshift squared, combined with ordinary effects related to how far light has to travel. The difference between these two dimming rates is exactly why a galaxy's bright, compact nucleus can remain detectable long after its surrounding structure has faded into complete invisibility. This is not some newly discovered, exotic quirk of physics. Astronomers have understood surface brightness dimming for decades, built into the fundamental mathematics of an expanding universe. What made the saguaro discovery so important was not uncovering a brand new physical principle. It was applying a well-established principle directly, concretely, to solve a specific, stubborn mystery that had been puzzling scientists for years. Here is why that distinction matters. Scientific breakthroughs do not always require inventing something entirely new. Sometimes the biggest breakthroughs come from recognizing that an old, well-tested idea applies perfectly to a brand new situation, one nobody had previously connected it to clearly enough. Researchers involved in the study were careful to frame their findings this way. Rather than claiming to have discovered strange new physics, they emphasized that this dimming effect had simply not yet been directly, empirically demonstrated using an actual example specifically tied to little red dots. The saguaro provided exactly that missing piece. Concrete, observable proof, rather than pure theoretical speculation. This distinction carried a broader lesson, extending well beyond little red dots specifically. It served as a reminder that objects appearing strange, exotic, or even physically impossible at extreme distances might sometimes be far more ordinary than they first appear. Once scientists find a way to study a similar object up close, free from the distorting effects of distance itself. With this physical mechanism now confirmed through direct demonstration, researchers turned towards stacking even more evidence on top of the saguaro's results, determined to see whether this explanation held up across independent studies, using entirely different methods and completely different objects. Good science rarely rests on a single result, no matter how compelling that result appears. Researchers understood that the saguaro discovery, while powerful, needed support from independent evidence before the broader scientific community would fully accept this explanation for little red dots. Fortunately, that supporting evidence had already been building for months, arriving from a completely different direction entirely. In June of 2026, a separate research team, led by scientist Vasily Kokorev, published results from an object nicknamed Glimpsy, a little red dot that happened to benefit from a rare natural advantage: gravitational lensing. Gravitational lensing occurs when a massive foreground object, typically a galaxy cluster, bends and magnifies light from a more distant background object, acting almost like a natural, cosmic magnifying glass. When a distant little red dot happens to align closely enough with one of these massive foreground lenses, its light gets amplified dramatically, allowing scientists to study details that would otherwise remain completely invisible. Picture trying to read incredibly small text from across a large room until someone hands you a magnifying glass powerful enough to bring every letter into sharp, readable focus. That is essentially what gravitational lensing accomplished for this particular little red dot, delivering the deepest, most detailed spectrum ever captured for an object of its kind. Using this dramatically amplified signal, researchers identified over 40 separate spectral lines within the object's light, each one acting as an independent clue about the physical conditions surrounding its central black hole. Every single one of those 40-plus lines lined up consistently with the same underlying model: a compact, actively feeding black hole, wrapped inside a dense, obscuring cocoon of gas. This mattered enormously because of sheer statistical weight. One or two matching clues might be coincidence. 40 independent, mutually consistent spectral features, all pointing toward the exact same physical model, represent an overwhelming, extremely difficult to dismiss body of evidence. Combined together, these two breakthroughs, the saguaro's direct, close-up demonstration and Glimpse's exceptionally detailed, magnified spectrum, formed a genuinely powerful case. One study proved the underlying mechanism directly, showing exactly how a normal galaxy disguises itself as a lone red dot at extreme distance. The other study proved the internal physics directly, confirming in extraordinary detail exactly what kind of object hides at the center of that disguise. Individually, either discovery would have represented a major step forward. Together, arriving within roughly a month of each other, they transformed little red dots from an unsolved, headline-grabbing mystery into a genuinely understood, well-supported scientific story, backed by both observed mechanism and observed physics simultaneously. With the core mystery now largely resolved, scientists could finally turn their attention toward an equally fascinating question. If little red dots really were young, actively feeding black holes, wrapped in dust and disguised by distance, what did they eventually grow up to become? Solving what little red dots are naturally leads to an equally important question. If these objects represent black holes caught in an early, furious stage of growth, something must happen to them as the universe continues aging. Black holes do not simply disappear. Whatever little red dots evolve into should still exist somewhere, hiding among the galaxies astronomers already study today. According to the framework built from the saguaro discovery, little red dots represent a specific, temporary phase in a much longer story. Early on, these black holes feed extremely rapidly, consuming surrounding gas at rates pushing close to their theoretical physical limits. That rapid feeding generates enormous energy, and it churns up thick layers of dust and gas, wrapping the entire system in the same kind of dense, obscuring material responsible for their reddened color and muffled X-rays. As time passes, that available gas supply does not last forever. Surrounding material gets consumed, blown away by radiation pressure, or simply used up entirely. Without a constant, overwhelming supply of fuel, the black hole's feeding rate naturally slows down. Less feeding means less generated heat and radiation. Less radiation means less surrounding dust gets kicked up and maintained. Gradually, the entire system begins clearing itself out. Picture a bonfire roaring violently right after being lit, throwing thick smoke and bright, chaotic light in every direction, before eventually settling into a calmer, steadier burn. As the initial rush of fuel gets consumed, little red dots may represent something similar, a black hole's initial, explosive growth phase, eventually settling into a calmer, quieter, longer-lasting state. That calmer, quieter state looks remarkably familiar. It resembles the supermassive black holes astronomers already study extensively across the more recent, nearby universe, including the relatively calm, mostly dormant black hole sitting at the center of our own Milky Way galaxy. This framework suggests something genuinely profound. The extreme, chaotic, difficult to explain objects scientists spent years puzzling over may represent nothing more exotic than an early chapter in an extremely common story, the birth and growth of supermassive black holes, a process every large galaxy in the universe, including our own, likely experienced at some point in its distant past. Researchers involved in the saguaro study framed this connection directly. Everything created in the early universe must evolve into something existing around us today. For years, scientists had almost no clear idea what little red dots eventually became. The saguaro offered the first, genuine roadmap for tracing that evolutionary path forward, connecting one of the universe's strangest early mysteries directly to the calm, familiar galaxies filling the night sky today. That connection carried an unexpected, deeply personal twist, one that reached far closer to home than anyone initially expected. Here is a detail worth sitting with carefully. If little red dots really do represent an early, active growth phase experienced by supermassive black holes generally, that story likely is not limited to a handful of strange, distant objects. It may be a chapter every major galaxy passed through at some point, including our very own Milky Way, Sagittarius A star, the supermassive black hole, sitting quietly at the center of our galaxy today, currently behaves almost nothing like a little red dot. It sits mostly dormant, feeding only occasionally, producing relatively little radiation compared to its dramatic, feeding frenzy cousins found throughout the distant early universe. But dormant does not necessarily mean it always behaved this way. If the little red dot framework holds true broadly across the universe, our own galaxy's central black hole may well have experienced its own furious, chaotic, little red dot-style growth phase billions of years ago, long before Earth, our Sun, or even our solar system's earliest building blocks existed. Picture looking at a calm, quiet grandparent and trying to imagine them as a wild, energetic teenager decades earlier, full of chaotic energy. Nobody witnessing their current calm demeanor would easily guess existed. That mental leap, connecting a calm present to a chaotic past, is exactly the kind of leap this framework invites scientists to make about our own galaxy's history. This idea reframes an object many people already know a little about, our galaxy's central black hole, transforming it from a fixed, unchanging feature into something with its own dramatic origin story, one connected directly to the same violent, dusty, light-bending processes scientists were only recently starting to understand through objects like little red dots and the saguaro. It also reframes little red dots themselves. Rather than existing as bizarre, disconnected curiosities floating somewhere in deep cosmic history, they become an early chapter belonging to essentially every major galaxy currently observable in the universe, including the one containing Earth, the Sun, and every person who has ever lived. This kind of connection, linking a strange, distant mystery directly back to something as familiar and nearby as our own galaxy's center, is part of what makes astronomy such a genuinely humbling science. The line between out there and right here turns out to be far blurrier and far more connected than casual stargazing might ever suggest. Still, connecting little red dots to our own galaxy's history remains a framework, not a fully proven certainty. Scientists were careful to note that plenty of open questions still remained even after the saguaro's powerful results. Understanding exactly how, and how universally, this evolutionary pathway applies would require significantly more evidence, gathered from many more objects, before the story could be considered fully complete. Even a breakthrough as powerful as the saguaro discovery does not close every open question surrounding little red dots. Scientists studying this population remain careful, deliberately, to describe their new understanding as one proposed pathway, rather than a single, universal explanation covering every confirmed little red dot across the entire catalogue. Little red dots, after all, span an enormous range of properties. They appear across a wide stretch of redshift, from relatively nearby examples down toward extremely distant ones. Their luminosities vary considerably. Their exact spectral details differ from object to object. It remains entirely possible that some little red dots follow the exact evolutionary pathway suggested by the saguaro, while others might have different origins, different surrounding environments, or different eventual fates entirely. Researchers involved in the study were explicit about this limitation. Additional saguaro-like galaxies need to be identified and studied before scientists can build anything resembling a complete census of little red dot descendants. One powerful example provides a proof of concept. It does not automatically prove every single member of an entire population behaves identically. There are practical next steps already underway. Researchers plan to search extensively through Webb's growing archive of observations, hunting specifically for additional intermediate distance galaxies containing little red dot-style nuclei, similar to the saguaro, but potentially offering slightly different details, environments, or evolutionary stages to study. Building that broader collection matters because it would allow scientists to study variation within the population, rather than relying on a single example. How does the surrounding gas reservoir influence a black hole's eventual evolution? How does the geometry of surrounding dust affect how quickly a system clears itself out? Does every little red dot eventually settle into a calm, dormant state, or do some follow more dramatic, more violent paths? There is also the broader statistical question of how common galaxies like the saguaro really are. Finding one such object through a combination of careful searching and fortunate archival alignment does not guarantee similar objects are easy to find elsewhere. Researchers need to determine whether the saguaro represents a fairly typical example of this transition phase, or whether it happens to be an unusually convenient, unusually well-positioned outlier. None of these open questions undermine the genuine progress made through this discovery. They simply reflect an honest, appropriately cautious approach to a genuinely complex scientific puzzle. Confirming a mechanism and confirming exactly how universally that mechanism applies across an entire diverse population are two different, equally important scientific tasks. What remains clear, even with these open questions still on the table, is that little red dots are no longer the impossible, physics-defying mystery they once appeared to be. They have become something far more interesting, a genuine, traceable chapter in the ordinary, universal story of how galaxies and their central black holes grow, age, and change across cosmic time. Step back from the specific details of little red dots for a moment, and a broader lesson comes into focus, one that extends across nearly everything the James Webb Space Telescope has discovered since it first opened its eye on the universe. Distance distorts, distance disguises, and before concluding that the universe has broken its own rules, scientists have learned it pays enormously to ask whether distance itself might be hiding a far more ordinary explanation. Little red dots are not the only strange, seemingly impossible objects Webb has uncovered in its relatively short time studying the early universe. Unusually massive early galaxies, unexpectedly mature-looking structures, and other objects challenging existing timelines have all appeared in Webb's deep field images since it began operating. Each new surprise briefly raised similar questions about whether standard cosmology could withstand this flood of unexpected observations. The saguaro discovery offers a valuable, broadly applicable lesson for approaching every one of these puzzles. Before assuming an object requires exotic new physics, ask whether ordinary physics, applied at extreme distance, might already explain the strange behavior being observed. Surface brightness dimming, redshift effects, and the fundamental challenge of observing extended structures across billions of light years. These are not new discoveries. They are well-established principles, sometimes overlooked simply because nobody had directly, empirically connected them to a specific, puzzling population before. Picture a detective working an unusual case, initially suspecting something wildly out of the ordinary, before eventually realizing the answer was hiding in a much simpler explanation all along, one that fit perfectly once examined from the right angle. Good science often works exactly this way. Confusion is not usually solved by inventing dramatic new rules. It is more often solved by asking sharper, more precise questions about familiar ones. This does not mean every mystery Webb uncovers will resolve so cleanly, or that cosmology never needs revision as new evidence accumulates. Science genuinely does update its models when overwhelming evidence demands it. But the little red dot story stands as a powerful reminder that patience, careful cross-checking, and a willingness to question your own assumptions before questioning the entire framework of physics remain some of the most valuable tools available to any scientist. Webb was built specifically to peer deeper into cosmic history than any instrument before it, and in doing so, It was always going to encounter objects nobody fully anticipated. That is not a flaw in the mission. It is exactly the mission working as intended. Genuine scientific progress rarely arrives without a period of confusion, contradiction, and uncertainty first. Little red dots pushed scientists through exactly that uncomfortable, uncertain process, testing patience, testing assumptions, and ultimately rewarding careful, persistent investigation with a genuinely satisfying answer. As Webb continues its mission, more strange objects are likely waiting in future data, ready to test that same careful, patient approach all over again. Little red dots began as an accident, a strange smudge noticed almost by chance in some of Webb's very first images. They grew into one of astronomy's most talked about mysteries, briefly threatening to upend decades of trusted cosmology. And they ended, at least for now, as a genuinely satisfying scientific story, resolved through patient investigation, careful cross-checking, and one lucky, well-positioned spiral galaxy sitting exactly where scientists needed it most. Along the way, this single mystery touched nearly every major idea in modern astrophysics. The stretching of light across an expanding universe, the extreme physics surrounding supermassive black holes, the delicate art of separating real signals from distorted, blurred, or disguised ones, and ultimately, a direct, physical connection between some of the strangest objects in the early universe and the calm, familiar black hole sitting quietly at the center of our own galaxy today. There is something worth remembering in how this mystery actually got solved. It did not require a bigger telescope or some dramatic new law of physics nobody had considered before. It required patience, careful archival searching, and a willingness to test theoretical ideas against a real, physical example once the right object finally turned up in the right place. That process, confusion, competing theories, contradictory evidence, and eventually, careful, hard-won clarity, is not unique to little red dots. It is how nearly every major scientific mystery eventually gets solved, whether it involves distant galaxies, hidden particles, or questions much closer to everyday life. Progress rarely arrives all at once. It arrives piece by piece, clue by clue, until enough evidence finally locks into place. Little red dots also carry a quieter, more personal kind of significance. Every one of these ancient, glowing points of light represents a supermassive black hole caught during its most chaotic, most formative stage of growth, a stage our own galaxy's central black hole almost certainly experienced too, long before Earth existed to witness it. In a very real sense, studying little red dots means studying a hidden chapter of our own cosmic origin story. The next time a strange, seemingly impossible object shows up in one of Webb's deep field images, it is worth remembering the lesson little red dots left behind. What looks broken, impossible, or physics-defying at first glance often turns out to be something far more understandable once scientists find the patience, the right tools, and the right example to look closely enough. The universe is not obligated to make sense immediately. It reveals itself slowly, one careful observation at a time. Little red dots were never really a warning that our understanding of the cosmos had failed. They were an invitation, a small, glowing reminder that even the strangest-looking mysteries usually have an explanation waiting patiently in the dark for someone determined enough to go looking for it.